A single star the size of Jupiter burns at 1/10,000th the brightness of our Sun. It has been burning for 2 trillion years. It will burn for 8 trillion more. The universe by then will be almost completely dark. Every bright star will have died. Every galaxy will have cooled. And this one small cold red dwarf, one of the last candles, will still be lit. This is a story about the brief window in which the universe is allowed to have stars. The Stelliferous Era. Stelliferous. Star-bearing. It's the name physicists gave to the chapter of cosmic history in which stars exist, because they had to distinguish it from all the chapters in which they don't. The era begins roughly 100 million years after the Big Bang, when gravity finishes pulling the first hydrogen clouds tight enough to ignite. It ends in about 100 trillion years, when the last red dwarf finally runs out of fuel. Everything you have ever seen, thought, loved, or wondered about, every poem, every war, every cell division, every supernova anyone has ever filmed, happens inside that window. Over the next half hour, we are going to walk the length of it. How long the lights stay on. Which stars burn out first. What it's like at the very end, trillions of years from now, when only the longest lived embers are left. And where we are standing inside the story right now. Imagine a single, enormous room. The lights in the room were turned on at a specific moment, and at a specific moment very far in the future, they will be turned off. Right now, the room is full of light. That is where we live. Physicists call this lit interval the Stelliferous Era. The first lights came on roughly 100 million years after the Big Bang. Before that, the universe was a dense fog of hydrogen and helium. No stars, no galaxies, no structure, just an expanding mist, slowly cooling in the dark. Gravity went to work on the mist. It pulled small irregularities tighter and tighter, until one of those tight places became hot enough to fuse hydrogen into helium. That was the first star. Point zero of the Stelliferous Era. The era ends, by most estimates, around 100 trillion years from now. That is a number with almost no traction in a human mind. 100 trillion years is roughly 7,000 times the current age of the universe. Everything that has happened so far, every galaxy that formed, every planet that cooled, every civilization that rose and vanished on worlds we will never visit. All of it sitting on top of the first 1/7,000th of the era's total run. Put another way, if the Stelliferous Era were a single 100-year human life, we would be about 2 weeks old. The lights came on 2 weeks ago. The lights will stay on for another 99 years and 50 weeks. This is a strange place for a species to find itself. The universe will spend almost all of its star-bearing history without us in it. And, more sobering, almost all of that history will look nothing like the sky we know. The blue-white stars you can pick out of Orion tonight are already the exception. They are the fast-burning young ones. They will be the first to go. What remains for the vast majority of the era will be a quieter sky. Fewer stars, cooler colors, longer silences. A room with the lights still on, but dimmed. We happen to be sitting in the brightest, busiest, most eventful moment the Stelliferous Era will ever produce. That is not an accident of luck. It's a consequence of what kind of star had to exist to make observers possible in the first place. a bright, fast-burning, medium-sized star, like the sun. The rest of this video is about what happens as the sky slowly empties out. In the core of every star, a slow fire. Hydrogen fusing into helium, 4 nuclei at a time, over and over, for as long as the fuel lasts. That fire is what a star is. When the hydrogen in the core runs out, the star is no longer a star. It becomes something else. So the lifespan of a star comes down to one question. How much fuel does it have, and how fast does it burn? The intuition most people reach for is more fuel, more time, bigger tank, longer drive. In the case of stars, this intuition is wrong. Spectacularly wrong. A blue supergiant weighing 40 times the mass of our sun does have more fuel, but it burns that fuel roughly 100,000 times faster than a sun-like star. The math lands somewhere unexpected. That enormous blue star lives for about 10 million years. Our modest, yellow, medium-sized sun lives for about 10 billion. A red dwarf, a cool, dim, half-hearted star at the very bottom of the mass scale, is fainter than the full moon at close range. It burns its fuel so slowly and mixes its hydrogen so efficiently that it will last up to 10 trillion years. 10 million, 10 billion, 10 trillion. A disparity of 1 million to 1, determined entirely by mass. This is the fuel clock. It runs backward from what intuition would suggest. The brightest stars die fast. The dimmest stars outlive them by factors almost impossible to write without exponents. Right now, in our neighborhood, the clock is running on all 3. The giant blue stars of Orion are already running out. Most will be gone before the sun is half its current age. The sun itself has about 5 billion years left in its main sequence. And the red dwarfs nearby, Proxima Centauri, Barnard's star, the vast majority of stars within 50 light-years of Earth, have trillions of years of main sequence life still ahead of them. This is why the sky is going to change. Not because new stars will appear. Fewer and fewer will, as the galaxy runs out of star-forming gas. But because the stars we can see now are running on 3 completely different clocks. The bright ones go first. The dim ones wait. Sometime around 100 billion years from now, the last star like the sun will finish its run. It will swell into a red giant, shed its atmosphere, and collapse into a slowly cooling white dwarf. The sun-like chapter of the universe will close. What remains after that is almost exclusively red dwarfs. Small, cool, stubborn. They will constitute essentially the entire lit sky in every direction for the next 10 trillion years. This is the long twilight. By this point in the story, the Milky Way will have merged with Andromeda, already on course to do so, roughly 4 billion years from now. The combined galaxy will have long since exhausted its supply of cold gas for new stars. Star formation, the process that has been refreshing the sky for 13 billion years, will have effectively stopped. There will be no new stars, only the old ones, getting older. Imagine standing on a planet orbiting one of those red dwarfs 10 trillion years from now. The sun in your sky is a deep red, not much larger than a bright coin held at arm's length. You do not need to squint to look at it. Your world is tidally locked. One face of the planet always pointing at the star. So sunset is a line on the map, not an event. The night sky is different too. Most of the bright, familiar stars, the O and B and A types, the blue whites and hot yellows, have been gone for trillions of years. The constellations, if your species invents any, will be drawn from dim red points. There are fewer of them. The galaxy is less full. And yet, remarkably, this era, not ours, is the statistical norm. Summed over the full duration of the Stelliferous Era, the typical moment looks like this: a red sky, a quiet galaxy, a single slow-burning star. We are the outlier, early and loud. Our sky is overstocked with hot young stars because the universe is still close to its beginning. Visitors, if any ever come, will arrive into a sky that does not look like ours, because the sky that looks like ours is a 13 billion year flash near the start. At some point, around 100 trillion years from now, the very last red dwarf will exhaust the hydrogen in its core. It will not explode. It will not collapse dramatically. It will slowly, quietly fade. When that star finishes, and there is no ceremony, no witness, just a number on a cosmic clock, the Stelliferous Era ends. The room the lights were on in, the universe turns it off. Beyond the end of the Stelliferous Era, a different kind of universe. Still vast, still expanding, but dark. Physicists call what comes next the degenerate era. Degenerate here is a technical word. It does not mean fallen or spoiled. It describes matter that has been crushed so completely that its electrons refuse to compress any further. White dwarfs, neutron stars, and black holes, these are what the stars leave behind when they finish. For a long, long time after the last red dwarf fades, the universe is populated almost entirely by these embers. White dwarfs slowly cooling from orange to red to black. The process takes a quadrillion years. Neutron stars, their surfaces occasionally flaring, drifting through empty space between the dead galaxies. Black holes eating the occasional passing remnant, growing slightly. This era lasts, by current estimates, around 10 to the 34th power years. A 1 followed by 34 zeros. If the laws of physics allow it, and it is still an open question, even the white dwarfs and neutron stars will eventually dissolve. Proton decay, a hypothetical process, would unstitch the baryons at the heart of matter itself, one by one, over time scales so long that the Stelliferous Era, in comparison, is a blink. After that, if it happens, only black holes remain. The Black Hole Era, a universe of empty space populated exclusively by gravitational wells, slowly evaporating via Hawking radiation over 10 to the 100th power years. And then, at some unthinkable future moment, the last black hole completes its slow evaporation and the universe enters the dark era. Nothing, or more precisely, very nearly nothing. A near uniform sea of cold photons and decayed particles drifting apart forever in an ever-expanding space. This is the ending no one is present for. It is tempting to hear all of this as grim. It is not exactly. It is simply a map. The map of what the universe mostly is when you measure it by duration. The Stelliferous Era, the lit room, is a tiny, brilliant anomaly near the beginning. Almost all of cosmic time is spent in the quiet that comes after. And yet, everything that has ever mattered to anyone, every observer, every observation, every this, happens in that anomaly. because only the anomaly produces witnesses. The Stelliferous Era is not just when the universe has stars. It is when the universe is watching itself. Step back. 100 trillion years of lit sky. 13 billion of it so far used up. The rest, the overwhelming rest, belongs to stars we will never see, on planets that have not formed yet, circling faint red suns that have not yet ignited. We are the early visitors to a very long party. The house is new, the lights are fresh. The host is still setting out the drinks. Most of what will ever happen in this room, measured in years, in observations and silent moments, will not be us. It will be something slower, quieter, dimmer, something we will not witness. But we are here. The lights are on. And for the few 100 trillion years the room will stay lit, we happen to have shown up during its brightest hour. If this one landed, there's a whole library of stuff like it. Thanks for watching.